Welcome back. In the previous lecture, we recognized the Bloch ball as the state space for qubits. In this lecture, we learn how qubit states respond to unitary transformations. So we are talking about qubits, and we have seen that the qubits are described by these Pauli operators x, y, and z. We combine them into a vector, which is a vector in three-dimensional space. And if we pick out a component of this vector, say in the A direction, another component in the B direction, then the product of two of these components, a product of, say, x and y, or any linear combination of x and y, is just a multiple of the identity, and a third component of the sigma vector, namely the one which is in the direction that is orthogonal to both A and B. So this is why we have a cross product here. Now, since the product of two sigmas is the identity of another sigma, the most complicated operators that we can have for qubits are multiples of the identity. So here A0 times the identity plus a component of the sigma vector operator, A dot sigma. So that's the general form of an operator for the qubit. The particular operator that describes the state of the qubit, the statistical operator rho, is a half times the identity and a half times this Bloch vector times sigma, where the Bloch vector is a vector that does not exceed unity in length. Then let's look at some particular operators for the qubits, those that change one basis to another. So those would be the unitary operators. So a unitary operator U is such that you take the adjoint, you multiply with U, you get the identity. And also if you do this in the reverse order, U times U adjoint. Now, if we have a U, then the U has to be such that it turns one basis into another. So let's just say that it maps the ket described by 1, 0 into a ket described by alpha beta. And then, of course, we need that the alpha squared plus beta squared is equal to 1, because we begin with a properly normalized column that goes with a ket of unit length, and we turn it into a new ket of with the same length. So this is why we need that the alpha squared plus the beta squared is equal to 1. And then it will map the 0, 1 column into a column that is perpendicular to this one, orthogonal to that one. And for that, we can take the column made of negative, the complex conjugate of beta and the complex conjugate of alpha, and we can easily verify that these two columns are orthogonal, which means that the U that we are talking about is represented by the 2 by 2 matrix, which has these columns as its columns. So that's minus beta complex conjugate, and there's alpha complex conjugate. And yes, I mean, if we now represent the U adjoint by the adjoint matrix, then that would be alpha complex conjugate minus beta, beta complex conjugate, and alpha. And we can check that the product of these matrices is such that in this order or in this order, it gives us the unit matrix. So now how would we represent a U of this kind in this particular form, where we write it as a constant multiplying the identity and a vector dotted into sigma? Well, for that, I will take these complex numbers alpha and beta and write them as their real part and the imaginary part. So I now have for beta 1 plus I beta 2, and these numbers appearing here, all of them are real. Not this beta, sorry. This beta is complex. Beta 1 and beta 2 are also real numbers. So here is the unitary operator represented by this matrix that involves alpha and beta, and here I have written alpha and beta and their complex conjugates in terms of these real parameters alpha 1, alpha 2, beta 1 and beta 2. And now we can take this apart such that we recognize the ingredients of the sigma vector operator. So first of all, I write the part that goes with alpha 1, and that is just the 2 by 2 unit matrix. Then let's identify what goes with alpha 2, or rather I times alpha 2. That's 1, 0, 0, negative 1. Then I will identify what goes with uh, uh, I beta 2, and that is the matrix that has 0, 1, 1, 0. And finally, I will write what goes with I beta 1, and what goes with I beta 1 is the matrix which has 0, I, and the negative I, 0. As we can check, I beta 1 times I is negative beta 1 here, and I beta 1 times negative I is plus beta 1 here. But now we recognize the matrices that we have seen earlier, and which we called X, Y, and Z. This matrix is the matrix Z. This matrix is the matrix X, and this matrix is the negative of the matrix Y. So the U then is alpha 1 times the identity plus I times beta 2 times the X operator minus I times beta 1 times the Y operator and plus I times alpha 2 times the Z operator, which now I recognize is of this form, so I can now just write U0 plus a U vector, I times a U vector, times sigma, where this U vector, the U vector has the Cartesian components of beta 2 and minus beta 1 and plus alpha 2, and the U0 constant that multiplies the identity operator, that is just alpha 1. So we have related the real ingredients of these complex numbers, alpha and beta, that we start with, to the coefficients that appear here, which are of this form, and the A vector that we meet here is actually I times a vector with real coefficients. Now, we said earlier that the unit length of these columns in the U matrix is guaranteed and requires that alpha squared plus beta squared is equal to 1. So that makes this column a unit column, it makes this column a unit column, it also makes this row a unit row, it makes this row a unit row. So if I look over here, well, that condition becomes, well, if I write it out in terms of the alpha 1s and beta 1s and of these real ingredients, then I have alpha 1 squared plus alpha 2 squared plus beta 1 squared plus beta 2 squared equals 1. And now if you look here, this just says that the U0 squared plus the length of the U vector squared, that this have to add up to 1. So a unitary operator, and this is quite general as a unitary operator is of this form with a multiple of the identity and a real vector multiplied by I dotted into sigma, and with the condition that the U0 squared plus the length of the U vector squared is equal to 1. So we have this expression for a unitary operator acting on the qubit cats and also on the qubit brass, written as U0 times the identity plus I times U dot the sigma operator, where U0 and U vector are real quantities, which are such that the U0 squared plus the length of U squared is equal to 1. Now the sum of two squares equal to 1, that's very reminiscent of the trigonometric identity that the cosine of some angle phi squared plus the sine of phi squared is equal to 1. And we will actually use this now to reparameterize the u. For that we write u0 equals to cosine phi, and the u vector then has the length of sine phi, so we write the u vector as sine phi multiplying a unit vector e. So e squared is 1. This is a vector of unit length. And now putting things together, our form for u that we are going to use from now on is cosine phi times the identity plus I times sine phi times E dot sigma, where E dot sigma is a component of the sigma vector picked out with a unit vector. So if the unit vector is in the x direction, we just get x. If the unit vector is in the y direction, we just get the y operator. If the unit vector is in the z direction, we just get the Pauli z operator. If the unit vector is in some other direction, we get a linear combination of x, y, and z. All right, so the unitary operator acting on qubit kits and qubit bras is cosine phi times the identity plus I times sine phi times a unit vector picking out a component of the sigma vector operator. So now, since this is transforming kits and bras, we can ask what's the effect on the statistical operator rho. So what do we get when we transform the kets in the ket bras that make up rho by u, and then have the adjoint operation acting on the bras? So this will then be a rho prime, and it will still be of the same structure. It will have the structure of 1 plus, and now it's S prime dot sigma after the transformation. We can immediately verify that this rho prime has all the properties that we request of statistical operator like rho. So we can verify that rho prime is positive, and the trace of rho prime is 1. But the question that I want to address now is, what is S prime? How does this unitary transformation change S into S prime? And for that we recognize that there is a particular direction in space specified by E. And so we have this direction E, and then we have the direction of the Pauli vector S. So let me draw this here. And as we can see, there is a component of S in the direction of E, and that component I will call S parallel. And then there is a component of S in a second direction, specified by a unit vector E prime, where the E prime is perpendicular to E, and that component I will call S perpendicular. So we have the S vector equal to S parallel times E plus S perpendicular E prime. And then there is a third direction that we get from the cross product of E prime and E, and I call that E double prime. And that vector, well, points from me to you. So if you use your right hand, thumb E prime, this is E, then the cross product is where my middle finger points, which is towards you. So what we need to work out is what's the effect of this unitary transformation on S dot sigma. So the S dot sigma is the S parallel E dot sigma plus the S perpendicular E prime dot sigma. And really, the E dot sigma, well, that's just E dot sigma. So the E dot sigma commutes with U. And so if I look at the transformation of U applied to E dot sigma and then U adjoint, well, that's just E dot sigma again. So which means that this parallel component will not be affected, but the perpendicular component will be affected. And if we work out the details, the S prime has the same as parallel component in the direction of E, but the perpendicular component is rotated, so it's now as perpendicular, but no longer in the direction of E prime. It has cosine 2 phi times E prime plus a sine of 2 phi times E double prime, which simply means that this vector S is rotated around the direction of E, so rotated around this direction by an angle of 2 phi. So if phi is 0, no rotation at all, this is just E prime, and we have the S vector as before. So it's just S of E prime. However, if sine of 2 phi is 1 and the cosine of 2 phi is 0, then we have rotated by 90 degrees around E, and the perpendicular component is now in the direction of E double prime, no longer in the direction of E prime. And so it goes, okay? So the S vector is S parallel times the unit vector E plus S perpendicular times the unit vector E prime. And now, since this E dot sigma, commutes with this E dot sigma, it will not be changed by the unitary transformation. So the S prime vector will also have S parallel times E. But this part, E prime dot sigma, well, that's orthogonal direction of E. So this orthogonal direction plays a role in this multiplication of A dot sigma, B dot sigma. Here it will be E dot sigma and E prime dot sigma. And so we get the cross product of the two, which will introduce a third direction, dot sigma. So we will get for the S perpendicular component, we will get the E prime, but that will pick up a factor of 2 cosine phi E prime, and there will be the third direction with sine phi 2 phi E double prime. And this E double prime vector, the E double prime vector is just the cross product of the E prime vector and the E vector. So in this picture here, it is a vector that is out of the plane that I have drawn, and namely the vector that points from me to you. So if you use your right hand, thumb in the E prime direction, first finger into the E direction, then the middle finger points in the direction of E double prime, from me to you. So the parallel component is unaffected. The perpendicular component gets rotated around the E direction, where the E prime direction is converted into a linear combination of E prime and E double prime. But of course it stays in the plane that is perpendicular to the E direction. So since this is a rotation around the E vector, as I just said, the length of the block vector should not be affected. So the block vector S prime should have the same length as the block vector S. So let's just take note of that. So if I have the S prime length, let me look at the square. So it's the F prime dot S prime product. Well, there's the S parallel squared, and then we have the S perpendicular squared, and that goes with the cosine of 2 phi squared plus the sine of 2 phi squared, which is another case of where we have a squared cosine plus a squared sine giving us 1. So the length of the block vector is indeed unchanged. S is proper for a rotation. In summary, a unitary transformation rotates the block vector of a qubit state, but does not change its length. In the next lecture, we consider successive rotations of this kind.